This is Matthew Gaskins. I have Ryan Schmidt and Josh Walden in my group, and what we're doing is numerical analysis project. So problem one is just linear systems. It's using system of equations to find independent variables x, y, and z, or x1, x2, x3, whatever you, however you really name it. It's arbitrary at that point. And so on Purple Math, I have an example right here of a 3x4 working it out completely. And so I'm just going to run my code right next to it step by step to see if we get the same values. And so if we run this step, we're going to display the matrix first to make sure everything matches up. And so we're going to go to the next step itself. And so we're just going to start in our for loop. And what our for loop does is the outer one's going to run column by column, and we're going to run up until column -2, so there's 4 columns. It's only going to run to the second. It's only going to run to the second column here, right here, because we just want to eliminate this 5, 1, and this 4, 2 zeros. So then we run matrix. We're going to run row by row after that, and our row is I plus 1 to the end of rows. So if I is 1, we're going to start off at this second row and work down in this first column. So we're just going to keep running step by step. So now what we're doing is we're taking this first row and we're dividing by the -3 to simplify it, multiply by this 5, and then subtract the 2, and we're going to create our new matrix. So now we create our new matrix. What we did is we simplified this first row, turned this -3, which is our leading coefficient, to a 1, multiplied by the coefficient of the row that we're going to manipulate, and then subtract the 2 to eliminate it and create a 0. So then we're going to run through again, and we'll do the same thing. And so this time same thing, we divide this by -3, create this -3 to be a leading 1, and then we're going to multiply it by whatever value of the row that we're looking at. In this case will be row 3, and then subtract the 2. And now the first column has the amount of zeros that it needs. So then we'll move on to the second column. And then, so next, what it does is it takes this entire second row and divide it by 10.33, and I can show you all the factor. This is what the row turns into be. It will be a factor row, and it turns into a 1. It just takes this leading value here for whatever row that we're using to eliminate underneath it. In this case will be 4.667. It turns this into a 1 and then multiplies it by this value, so we can subtract them and cancel them out to get our 0. So at this point we have our upper triangular form of this matrix. So we're done with that for loop, and then that will be our new matrix. So now what we're doing is we're checking for conditions. If this entire bottom row was zeros, it has infinite many solutions, so none of the variables have unique solutions. The next condition is if this left term here that I have highlighted is 0, but this one isn't, it's any real number, at that point that the solution will have no unique solutions because all of them would be undefined. So now that, since both of them have zeros, we know that they're going to have unique solutions, so we're going to pre-allocate a column vector or a row vector full of zeros. We're going to fill it in. So what we do is we start from the bottom row and work up. So now what we do is we take this left term and take this term and divide it by the left term, and we're going to find our x3. So we do that. What we do is we find that we have 0, 0, 1. So now we just have to find x2 and x1. So what we can do is we're going to start in our for loop. It'll do it again, and this is what our x is. So it works from the bottom up. We found x3, now we found x2, and now we found x1, and now we have our row solution. And then we have our fprintf for loop to actually display it for y'all whenever we run the actual code. So that is basically the first one. Now that is an ideal solution. There can be problems if we wanted to run it that way. One of the main things is that we needed to be able to manipulate the row in case there was a 0. Since we're trying to find zeros underneath it, for some reason if there's a 0 on the diagonal, basically on above the diagonal or on the diagonal, we would have to be able to swap the row. So in this case, we created a condition. And let me get back to my, just for the video, we have this one. Run section, and then for this one, what I'm talking about is 0, 2, 5, 4, is there's going to be a 0 on the diagonal itself, and the diagonal is the 2 to the 2 to the 1. It's a diagonal, and everything underneath it needs to be 0. So now we're going to run it step by step and run through the condition. Now, since we know that the leading value is a 0, we need to swap it with the next. We need to find the row, the first row that is a non-zero. In this case, will be row 3. And so it goes into our if conditional statement, and it's going to create a temporary matrix to swap them around. And so now our new matrix will have the first row on the bottom and then the last row on top. And then we'll start and run through with our Gaussian elimination. But since there's zeros here, it's just going to run through them, but nothing's going to happen. And basically, it'll just have to run until it gets to the second column. And so it ran, and it only had to do Gaussian elimination for one row one time and produce our new matrix, and it'll find our. Now it's going to start using back substitution to solve for our independent variables. And it goes through and it solves them using back substitution as in the first problem. Now there are the other cases is when we get infinite many or no solutions at all, and in that case that the program itself will just stop and will not let you run anymore. It'll just end the program using the error function itself, so you can't run it anymore. So if I wanted to just run that example for y'all, I'm going to just type the matrix in and run it. -2, 1, 5, 12, -7, 7. It's just saying your matrix will have no solutions because in the uptry function itself, at the very end before it moves on to allow you to use back substitution, it checks the rows. In this case, it has a 0 and a 1. And the way we find the way you start with back substitution is by using the x3 or the third column value and then dividing the solution by the x3 to figure out what x3 is equal, and then you'll plug it in. In this case, you would divide 1 by 0, which would become undefined, and then the rest would just be a leading undefined train until the very end. So none of them will be not a number, and there's no unique solution to solve this matrix. Now for the bisection method, which is number 2, that is numerical analysis. Bisection method is a slow process, and the reason it's a slow process is because you're using approximation to find a root for the crossing basically on the x-axis. And so here, there's a little demonstration. We have a function. This looks to be a parabola, and when it starts, you start really big, and you choose 2 bounds. Wait for it to restart. Yeah, so you start really big, and you work from side to side by finding the midpoint between 2 bounds. So, and in this case, what we're using is our first function is bisect root. And so it starts by checking the bounds that you enter by plugging them into the function. For example, when we plug in the bounds for the function, if both of the outputs become both positive or both negative, there's no way for there to be a root because it didn't cross the x-axis. And root is when a function crosses the x-axis, and that's when y equals 0. No, x equals 0. I'm sorry. Y equals 0. Y equals 0. I want to make sure I get that out straight. And so while it's running it, it's a slow process because you're using approximation and then just working your way in until you get into an acceptable error percentage that's off from the root. So it's not always it's not 100% accurate. It's more 99.9% accurate. And so the first thing that we do is we start off by entering our C will be some matrix, or it's going to be a vector, and it has the corresponding x cubed, x squared, x1 coefficient to follow for that function. Then what it does is it finds the midpoint. It'll find the midpoint and plug the midpoint in, and then see if that is acceptable error. If not, it'll plug it in, find if the output by plugging the midpoint into the function is positive or negative. If it is positive, the midpoint will become the new upper bound. If it is negative, it'll become the new lower bound. And then it'll continually do this by running through a loop, checking to see if the error is less than the maximum acceptable error that is inputted by the user. So we're going to run the test case solution that is provided on this project. And so we have 3, 14, 26, 1. So this will be 3x cubed, 14x squared, 26x plus 1. That's our function. And then the maximum error allowed 0.001 to try to get it as close as possible. We're going to guesstimate -1 and then +1 as our lower and upper bounds. And so as you from the number of iterations predicted for the root, it kind of gets closer and closer, but it has an asymptote. It never completely gets to, it'll never completely hit 0 because it is a slow method and it's not 100% accurate. It's just going to get as close as possible, but it will not be completely accurate. So it's going to follow this path all the way until infinity, but it will never touch 0 because it's based off a maximum error percentage. So we have the root at -0.04, which as our root is correct, and then the maximum error is the same, but the number of iterations is 11. So it took 11 run-throughs to find the root itself. So then our bisect root is finding the difference between the estimated root at iteration and the resultant from the bisection root. And it's a kind of a copy and paste, but you change a little bit. You just have to find the difference. The best way to describe it is find the difference between each iteration's approximation of the root and the final approximation of the root. And we're going to plot it as a function. So the only conditions on the bisection root is that when it comes to your bounds, if your bounds don't enclose a root itself, you'll have to re-enter a root each time. If you correctly guess bounds for a function, it'll run for a certain number of iterations, plot the two graphs, and it'll display the root, the max error, and how many times it took to actually get the root. So overall for everything, I think the project itself went pretty smoothly. I think that the first problem was a little bit easier than the second problem. Bisection method is a slower method. It's definitely not as efficient as just plugging it into a calculator, because you will never get 100% accurate. You'll get as close as possible, but up until the last decimal, it'll not be 100% accurate.